Okay. Now check this out. Lemmiux van Rudolph, or you can say Rudolph reagent. Okay. The other day we have seen Lemmiux Johnson reagent or Lemmiux Johnson oxidation. Now, what is this reagent? Let us see. A small change or a small difference. Here we have potassium permanganate and sodium periodate mixture. See, Lemmiux Johnson's reagent is osmium tetroxide along with that sodium periodate. Only difference is in this reagent we have potassium permanganate in place of osmium tetroxide, right? And of course there is a small difference also. Let me give you the basic reaction. Considering this particular reagent, this particular substrate with this reagent, okay, see from this area we get a ketone. Okay, and from the other area we know we get carboxylic acid. So this is interesting here. See, with Lemmiux Johnson, we took the same reagent, but here we got an aldehyde. But here, in this particular case, I mean, with Rudolph reagent, we got an acid. Okay, so this is the difference. Let me actually go for a very interesting example, taking both into consideration at a time. Okay. Now, supposing if this is taken into consideration, let me take this example. So this is, of course, cycloocta, you can say octene. With potassium permanganate, sodium periodate, we get, look at this. Okay, you just cut it here and see from both the areas, from these two, we get carboxylic. It's like from this area we got carboxylic. Yes, you got only one hydrogen connected to the double bonded carbons. So, of course, we get C double bond OH. Even from this area also, we get the same. Hope this is clear. So, with Rudolph, it's carboxylic acid. Of course, from this area, we get ketone, but we don't have any alkyl group attached to the double bonded carbon, so we got carboxylic. Now, when the same thing is taken with the same sodium periodate along with osmium tetroxide, we get aldehyde. So that is the basic difference. Come on. This, you take it up to this. C double bond O, just a hydrogen. C double bond O, just a hydrogen. Now this gives you maximum clarity. Come on, check this out. What is this? This is, of course, Lemieux, Van Rudloff, sorry, reagent, whereas this one is Lemieux Johnson reagent. See the difference. It's very interesting. In general, in organic chemistry, reagents used for a specific purpose are very important. Okay. Now let us go for some other reactions. In fact, some miscellaneous reactions. Let's see them now. Okay. Now, let me give you the reaction with NOCl. Let me call it addition of NOCl. You know, this NOCl is called Tilden reagent. Remember, this is Tilden reagent. Okay. Now let me give you the example. Take propene. See, when propene is treated with this particular reagent, okay, NOCl, okay, NOCl is called Tilden's reagent. Now with Tilden's reagent, what do we get? See, it's basically forming the cation and anion. That is very important. Cl gets negative charge and NO gets the positive charge. That's it. Here it is again following Markovnikov addition. When I say Markovnikov, you're all very, very clear about the thing that the negative part of the reagent adds on to that double bonded carbon having a less number of hydrogens. Okay, that's it. So let me just do this. Okay, this one goes here. Here you get a negative charge, and here a positive charge, of course. Okay, now the other thing is this. Very simple. These are all simple reactions, miscellaneous ones. CH3, CHCl, right? Then CH2, N double bond O. You know, this is nitroso group. It's called a nitroso group. Hope you all know that there is a kind of tautomerism called nitroso-oxime. Look at this. See, as and when this goes here, becomes a negatively charged. This one becomes positive. Now, when this actually attracts, just a second. So, as and when this abstracts hydrogen without the bonded pair, this one goes to the rescue of the positive charge. This is what we call tautomerization. Now, As a result of this, we get oxime, CH3, CH, Cl, CH, then double bond, N, then OH. Okay, so this is called oxime. So this, of course, is nitroso-oxime kind of tautomerization. Okay, so this is how alkenes react with the Tilden's reagent. Okay, next. Now let us take some other reactions. These are all very simple. Now suppose if we consider the addition of ICl. ICl in the presence of, say, ZnCl2, which is a Lewis acid. Now, of course, Cl minus, I plus. Chlorine is more electronegative, right? Now, as usual, according to Markovnikov, let me write that. Negative to positive, negative to positive. Okay, CH3, then CH, to which Cl is added, then CH2I. That's it. So Markovnikov addition of I plus and Cl minus. Let me also give you, of course, regiochemistry is Markovnikov, which is already given. Coming to stereochemistry. Stereochemistry is, of course, anti-addition. Anti-addition, which involves iodonium ion. See, the reaction will be similar to the addition of halogen, Br2, we have seen, where the reaction involves the initial formation of cyclic bromonium ion or cyclic halonium ion in general. Same is the case here. Even here also, the mechanism involves the formation of iodonium ion. Hope that is clear. So this, of course, is regiochemistry. Directional nature. Next, take addition of alkyl halide. Let me give you this. See, propene reacts with, say, methyl chloride in the presence of anhydrous aluminium chloride. Again, a Lewis acid. See, Lewis acids are generally meant for getting the electrophiles. See, in this case also, it can be written as this. The same thing, again Markovnikov. Come on. Yes. Uh, this one has to be from the negative to positive. Nucleophilic to electrophilic. Come on. CH3, CH. We got Cl here. Then there is a CH2. Then, of course, a CH3. Right? So this is the addition of alkyl halide. Very simple. Okay. Now we'll go for the addition of acid halide. So this is an acid halide. Come on. Now when the same propene is treated with, say, acetyl chloride or ethanol chloride, again, in the presence of anhydrous aluminum chloride. See, even here also it will be Cl minus and CH3 C double bond O plus acetyl carbonium ion. Come on. Very simple. Okay. That's it. Follow Markovnikov. CH3, CH, Cl here, CH2, then C double bond O, CH3. I need not say, but still. It's, of course, Markovnikov. Okay. Then let us take this. A thiol, but a hydrogen is replaced by chlorine here. pH SH is phenyl thiol, but that hydrogen is replaced by chlorine. Come on. Same again. See, this, of course, is Cl minus, then S plus. Simple. CH3, CH, Cl, CH2, yes, pH. Even in this case also it's Markovnikov, what we followed. And of course, the addition is of anti-type. I mean the stereochemistry. Regio is Markovnikov, stereo is anti-type. Next. We'll take some other miscellaneous reactions. See, when we go for the addition of cold concentrated sulfuric acid, we have already seen dehydration using concentrated sulfuric acid followed by heating in the preparations. But this is the addition of cold concentrated sulfuric acid to an alkene. Again, the same thing. It's again Markovnikov addition of H plus and HSO4 minus. Come on. Okay. Yes. See, we get, of course, a hydrogen to this. I mean, H plus is added to that. And here it will be this. O, S, double bond O, then OH. Look at this. This is HSO4 minus what is being added as per Markovnikov. Okay. Next. Let us take the dimerization of alkenes. Propene with H plus. Of course, a Lewis acid. You know, in this case, let us take it directly. Hope you understand. Make negative and positive as usual according to Markovnikov. Now, what do we get? CH3. Yes, here we get a positive charge, and then this CH2 minus will become CH3. Now, this carbocation, which is a stable one, again combines with another molecule of propene. Look at this. Go for the addition again. Negative to positive. What do we get? One second. CH3. Let me write it here. CH3, CH. Then here you got a CH3 again. Now this, see, if you want, I can show you the negative and positive charges. Here we get a positive charge, right? And here, of course, we get a negative charge, isn't it? The negative will now combine with the positive. Hope you understand. This is according to Markovnikov. So let me add this CH2. I mean, I've added this CH2, right? Then CH, of course, this CH will have a positive charge. Then the CH3 that is already there. Okay. So now for convenience sake, And of course, to get something which is more substituted, let me take it this way. Now this will go to the rescue of the positive charge, and of course the H plus catalyst what you have used in the first step will now go out because it's a catalyst. Come on, CH3, CH, CH3, then this CH double bond, CH, CH3. Okay, I think I'm okay. Right. So that is how the dimerization occurs. We can take any number of examples, but the mechanism will always be the same. Next. Let us go for iodolactonization. Interesting reaction. Take this particular substrate. Now, when this is treated with iodine in the presence of sodium bicarbonate or of course potassium bicarbonate, we get a compound of this type. Will give you mechanism to make you understand this. You know, cyclic ester is called a lactone. Hope you know this. Simple. Now, initially, okay, we'll see the mechanism now. C double bond O. Let me take this as O minus. Because anyway, we are using the bases. They, of course, abstract this H plus. Okay, so that is how we can take COO minus. Then it is the addition of iodine across the multiple bond to form a cyclic iodonium ion kind of thing. Is that right? Now, as and when this negative charge attacks on this carbon, okay, this will go off. Okay, that's it. I think we got our product. This. Anyway, this is C double bond O, this CH2, then this I. That's it. Okay. But remember here, the addition is anti. If you want to show that, you can show it this way. Then, of course, this will be like this. So this actually shows the stereochemistry. Anyway, Regio is already written. Regio. Here the attack is according to Markovnikov. Right. Can be seen that from here. This is where it has attacked. The negative has attacked at the carbon of the double bond that had a less number of hydrogens. Right. Now coming to stereo, even that is clearly visible. It's anti. Right. So this is iodolactonization. These are all miscellaneous reactions. Of course, can be understood based on the mechanisms what we have previously seen, but still we are taking all of them one by one. I think this is clear. Okay.